Hello everyone, this is lecture 6 of heat transfer. Last time I talked about the derivation process for heat conduction equation through infinitesimally small element. And I strongly suggest that you guys actually become well acquainted with this derivation process. Don't be scared and try to come up with a reasonable process. And the element we dealt with last time was extremely small element that looks like a cube, which has the dimension, three sides of dx, dy, and dz. And we considered the amount of heat flux that's going into the system and the amount of heat transferred out of the system as well, and the heat generated out of the system, and the resulting heat transferred amount will be used, transferred and the heat generated amount will be used to change the temperature of this material, right? And if you use such kind of concept reasonably enough, you can come up with a beautiful equation right away, the conduction equation. So the first topic we're going to deal with today is actually, we change gear a little bit, and we are looking at cylindrical coordinate system rather than this Cartesian coordinate system, and try to come up with a equation that is specific to this Cartesian coordinate system. By the way, I'm walking through the engineering building 301. Looks like not many people here because of the coronavirus. I hope everybody's safe and doing good. And soon enough, I hope we can get together and meet face to face and enjoy this nice discussion. Okay. Okay. So, as a good example of using the concept of electrical circuit analogy on the thermal analysis, let's try an example problem on your textbook. Please take a look at page 118 of your textbook, example 3.4. And this is a very interesting example indeed that deals with the carbon nanotube. And what is carbon nanotube? Well, I think I need to explain some background about this carbon nanotube and graphene as well, and also how can you test this carbon nanotube. The people are using microstructures made of silicon, and so I also need to explain how we can actually come up with the silicon microstructures as well. But right before that, anyways, let's take a look at this problem, okay? So we need to look at page 18, right? Page 18, and example 3.4, all right? And if you take a look at this example, well, they actually use silicon nitride microstructures to test the thermal characteristic of carbon nanotube. Well, so what they did was actually somehow, I say somehow, I'm going to explain soon, they made a microscale device. What is microscale device? I'm going to explain soon. Okay. With this silicon nitride structure. What is silicon nitride? Well, I guess I need to explain later on. I cannot, explain too much today because of the lack of time. Okay. So this is top view of the drawing appearing on your textbook, page 118. So not 18, but 118 to page 198. Okay, and you have this little island structure right here, supported by this thin beam, and they actually have. So if you take a look at the cross section of this beam or the bar, it will consist of silicon nitride and platinum. So this part, the core part, is really the platinum structure. Platinum, you know, the metal, right? And this shell or the exterior part is silicon nitride. I'm gonna use SN to stand for the silicon nitride structure, right? And the size is amazing. This is really small. This size is only 3 microns, and the thickness is 0.5 microns. What is 1 micron? 1 micron is 1 million times smaller than 1 meter. You see, this is indeed very small structure, right? If you take a look at this cross section, you know. So there's a platinum wire going through the center of the shell material, which is silicon nitride. Okay, and both structures have the same cross section. Okay, so there are platinum wire going through, and what they do is actually they use one of these structures as a heater, so that there might be probably some kind of a heater pattern in the middle. Okay, I'm gonna delete it. So it will produce the heat, which is temperature, TH. Okay, and the length of this whole structure is 250 microns. Again, so we call this supporting structure. Supporting structure. So I'm gonna use this length as L supporting. So L supporting is nothing but 250 nanometers. All right, and they heat up one side, elevate the temperature up to TH, and the surrounding area, all surrounding area, the temperature is maintained as T infinity, which is 300 degree Kelvin. 300 degree Kelvin is reasonable, right? It's like 27 degrees Celsius, sorry, 23 degrees Celsius, right? And TH, we really don't know the temperature. We're gonna find out about it. And TS is the temperature on the other side where we don't heat up. And T infinity again here is 300 Kelvin. You see that? Okay. So why does this temperature TS occur? Because they will put a little carbon nanotube here across the gap. Okay, and heat generated from the left hand side will actually migrate to the right hand side through this carbon nanotube. Okay, and the gap size of this carbon nanotube is 5 microns. 5 microns. Okay, so I would put the L carbon nanotube as 5 microns. Okay, just to give you an idea about uh, the size of a micron, well, your hair, if you just pull out and measure it, ranges from 50 to 100 microns. So it's a really small dimension, right? So if you talk about 3 microns, that's really small. If you talk about half of a micron, 0.5 microns, that's really small indeed, okay? And the gap size is only 5 microns. Well, the thing is, you know, this carbon nanotube dimension, this carbon nanotube, this is carbon nanotube. What is carbon nanotube? I'm going to explain soon, okay? Dimension is only, well, let me find out from the textbook, 14 nanometers. So it's a really small, right? What is 1 nanometer? 1 nanometer is 1,000th of a micron. So it's 1,000 times smaller than a micron. So it's 1 times 10 to the minus 9 meters. 1 billionth of a meters. 1 billionth. Okay? So it's really small. It's only 14 nanometers. Okay? And what happens is that the heat generated on your left hand side to elevate the temperature TH, which is unknown, will be transferred to the right hand side through this very thin carbon nanotube and elevate the temperature up to TS. What is TS? Right here, TS is 308.4 Kelvin. Yeah, so it's pretty high temperature compared to the room temperature, compared to 300 degree Kelvin. Remember, T infinity was 300 degree Kelvin. This temperature is elevated through this little structure. Can you believe it? So people are wondering how much value does this carbon nanotube have in terms of the thermal conductivity. So they are wondering what kind of thermal conductivity this carbon nanotube has. By the way, the heat generated from the right hand side, Q, heat generated on the right hand side, Q, was 11.3 microwatts according to the textbook. 11.3 microwatts. How can they measure it? Yeah, the current flowing in, the voltage, right? Power delivered, and you can roughly estimate how much power has been delivered actually, and that is the power used to provide this heat on the left hand side, okay? And that heat will actually be transferred through this carbon nanotube and go to the right hand side, right? And so what kind of other things do we need to know? Well, the heat generated here will not only go to the right hand side, but it will also go up and down, right? And the right hand side, it will also go up and down. So these 4 elements, 1, 2, 3, 4 supporting element will provide the same thermal resistance, right? And the carbon nanotube will provide another kind of thermal resistance. Okay, so thermal conductivity of the platinum here is going to be 71.6 watt per meter according to your textbook, and thermal conductivity of silicon nitride will be pretty low, only 15.5 watts per meter. So we got pretty much everything ready here, okay? But before we start this analysis, let's take a look at what kind of material the carbon nanotube is, and what kind of structure, this silicon nitride structure is, how we can manufacture it. So I'll stop the video a little bit and go to my lab and introduce you guys to the fun story about the fun world of nanostructures, and I also introduce you guys to the exciting the world of microfabrication. Okay. Well, before making our journey to my lab and clean room facilities where they actually manufacture these microscale devices and deal with these nanomaterials, uh, let's take a look at my background a little bit. I'm the one actually who developed the microscale testing stage for pulling test of this carbon nanotube indeed. So for example, if you take a look at the website and try to find out what kind of test you can do with these structures. Well, let's go to the Google and try search material pooling test. What kind of devices do you use actually? You use something like this, right? This kind of devices, right? You see that? You see some, well, it's too small. Right? Something like this. It's a mechanical tester. You put some kind of a specimen in there and then pull until they break. And you measure stress, strain, or the force and elongation that represent the stress and strain. And you can see how this material behaves. Well, years ago, we have wanted, myself and my colleague and my students, we have wanted to test this little teeny tiny carbon nanotube. How small is it? It's like tens of nanometers. How long is it? It's like a couple of microns. So it's very hard to test them actually with this kind of material, this kind of a machine, right? You cannot even see that, right? So, and also we have wanted to watch this elongation process in real time. But how can you do that? Just simple microscope cannot do that actually because it's too small, invisible under the microscope, even under the microscope, because of the something called diffraction limit. I'll talk about this diffraction limit later on. So people use scanning electron microscopy actually. Scanning electron microscopy to look at the motion of the whole thing. So our task is to create the device, as small as this nanotube, comparable to the size of this nanotube, and then so small that you can put into the scanning electron microscopy and supply the current or voltage, whatever, to create this motion. So we need this small machine that can actually move inside the scanning electron microscopy. So years ago, we dealt with this problem. So if you go to the web and then punch in, for example, say carbon nanotube stage, testing stage, and my name, Jung Lee Woon. You'll find out something, some kind of search results. And among these search results, probably you can see my name and research date. Let me see. Does it show up? It's right here. You can pick up one of the papers. And if you take a look at this paper, it says in situ
Mechanical Testing of Templated Carbon Nanotubes, written by myself, John Lee, and my colleague, Vladimir Ruoff, and the student I co-advised with Ruoff and myself, Sharon Lu. And just take a look at some of the pictures. Probably I can provide some explanation what really is going on. So this is a micro scale stage. Look, the size of it is something like only tens of microns. And this long beam is just a mechanical beam, something called amplification beam. And these thick beams, thick bars, are the bars that will expand when you apply the current. Apply the current, temperature will rise, and there's a material constant, right? Material constant, what is it called? Thermal expansion coefficient. Because of that, this part will elongate. And look what will happen. If that part elongates, if this part elongates, this part will elongate, and this bar or this island is supposed to retract, move back, try to zip out. This guy will move back actually. And this is the fixed part. So relative to this island will move out. So if you go down a little bit, you can take a look at this picture. Relative to this island will move out. Now our task is to fix or place the carbon nanotube in between. And I'm not going to go through this detailed technology because of the lack of time, but somehow we use a very interesting technology, something called fluid-based self-assembly technology, to assemble this carbon nanotube in between these microscale stages right here. Microscale. Look, this is only 20 micron bar, so it's really small. You can see carbon nanotube. You can see this carbon nanotube because we took the picture inside scanning electron microscopy. Okay. So if you look at a little bit more detail, look, we were even able to fix this carbon nanotube at both ends, right here, and then this is a stage. You know what happened? As I explained, this guy will retract as you apply the current inside the scanning electron microscopy. So you can actually look at this motion in real time and see how this carbon nanotube will break. And you can take, you can measure the force with different mechanism, so that you can actually measure retraction amount, elongation of this carbon nanotube versus the force. So we can do mechanical testing of this nanotube inside this, with this tiny device inside scanning electron microscopy. So now is the time to take a journey to my lab to see what kind of material the carbon nanotube or the graphene is, and we'll continue our journey to Semiconductor Research Center to see how this microscale machine is created there. So your heat transfer model can be expressed in a concept that's equivalent to electrical circuit. Temperature difference is much more like a voltage, and the current is much more like the heat transfer. So you can introduce thermal resistance as a way of this heat transfer is related with the temperature difference. So there are a number of examples in your textbook, but one of the examples I chose today is about the carbon nanotube. What is carbon nanotube? Carbon nanotube is much more like a rolled sheet of graphene. What is graphene? It is carbon formed in a grid shape,
called phenol rings, the hexagonal rings, and depending upon the direction, well, it's just at an ideal state, you can obtain a single sheet of carbon that is called graphene. And Andrea Jaim and some of his colleagues a number of years ago at the Manchester University got the Nobel Prize because they were able to separate this single sheet of graphene and measured their electrical physical properties. So carbon nanotube is again the rolled form of this graphene, and a number of years ago people found some very interesting phenomena, very interesting characteristics of carbon nanotube. They have a very special chemical characteristics. They have very special mechanical characteristics such as tensile strength approaching to the ideal limit of 1 gigapascal. So based on that, people started thinking about amazing material as light as a glass, a piece of glass fiber, and stronger than the strongest steels on earth. You can construct a superstructure with that. And people started thinking about biosensors. They can actually use carbon nanotubes, and they published a lot of materials on these nice papers, Nature, Science, and other things. And one of the interesting characteristics of this carbon nanotube is its thermal characteristic, and more specifically, heat transfer through this carbon nanotube, depending upon the direction, can occur very rapidly, very efficiently. Amazing property is possible in terms of thermal conduction. So today we'd like to look at an example that uses this concept of electrical circuit analogy to analyze the carbon nanotube. By the way, where do we have carbon nanotube? By the way, this is the one of my lab spaces, my graduate school laboratory spaces. You're looking at my researchers. Hi, Robin, and hi, Hyunjae. Okay, and Hyunjae brought some powder of. It's not exactly carbon nanotube. It's graphene, but very close relative of carbon nanotube. So what you're looking at here, just the black piece of solution. Why is the solution? Because Hyunjae, actually, how did you prepare this sample?
I mixed the graphene powder with polyethylene glycol.
Polyethylene glycol.
Yes.
PEG, polyethylene glycol, and you can obtain this black, material. Very dark, extremely dark. Actually, one of the darkest material on earth. Right? And we are developing some nice sensor based on this material. I'll talk about the sensor later on. But today, with me and you guys in class, we are interested in doing some analysis of this carbon nanotube thermal properties using our concept of electrical circuit analogy. Okay? So, how do you make a structure that's very, very small that can hold this little tiny nanostructures and do some kind of experiment like pooling test, like the pooling test you guys are doing in solid mechanics classes, and heat transfer test like the one we are going to analyze today in class? Well, it is the silicon structure that can actually carved into micro scale devices, even nanoscale devices. They can actually move, they can transfer the heat, they can provide electrical energy, and they can do a lot of works They can also be connected to a chemical system. Well, the secret lies in the manufacturing of the silicon. And here I'm at the place on our campus where you can actually manufacture the silicon structures. And this place is called right here. You can see that? You can see that right there, right? So Inter-University Semiconductor Research Center, ISRC. That was founded in 1985. 1985 is the year when I entered the school. So there are a lot of stories behind this technology, and there are a lot of fun stories as well, like this nice guy and the great guy, this great Korean, who developed historical element in the semiconductor industry long ago. I have a lot to talk about this guy, but later on. We don't have enough time today. So here in the Semiconductor Research Center, I would like to show you, what kind of devices are made using what kind of equipment, and what kind of process you can think about. 안녕하세요. 네. Okay, so I'm inside the Semiconductor Research Center. This center has the clean room where you need to have a tight control over the dust particles for IC industry, semiconductor industry. As you can see here, there are a lot of complicated equipment inside this clean room, for research purpose. If you go to industry, they have a gigantic machine which actually can be used to develop and manufacture, memory devices, computer chips, all sort of interesting things. So these are the devices that people use. This is the entrance to the clean room. You have to wear the clean room suit and wear the mask before going into this place. This is the place where actually we manufacture the silicon devices, silicon MEMS devices. We call it MEMS, micro electromechanical systems. So look, this is the space where people manufacture these small devices. Okay? Again, the other entrance, and we call this yellow room because people use photosensitive material. They want to eliminate UV light, and the result of eliminating UV light, you have a yellow light. And this is the equipment room where actually we look at our samples. So one of the equipment people use inside here, 안녕하세요. 1초만. It's called SEM, Scanning Electron Microscopy. 이거 SEM 맞죠? 네, 맞습니다. Yeah. So if you open this device, people use the electrons to look at a small structure. Why electrons? Because they have less diffraction. I'll talk about such diffraction later on. Basically, using this kind of devices, you can take a look at teeny tiny materials and the teeny tiny devices as well, like carbon nanotubes and the microelectromechanical systems. The trouble is that you have to open this up and then put your sample inside. You got nothing to do, from then on. So basically, we want to provide electrical current, make the device move, and while the device is moving, we need to look at the sample behavior inside in real time. Because of that, we developed this device called movable microstage that can be actually put inside to this SEM, scanning electron microscopy, okay? You are looking at the history of the semiconductor business, starting from light emitting devices, sensors for the robots, and many other applications, and more than anything else, the memory devices that were developed in some commercial, field in South Korea, right? And so if I summarize the introduction, prolonged introduction today, the device that you are going to analyze in your class today is the outcome of many of your seniors in real research field. And because of their prolonged accumulated result of the research, we are able to look at this nice results that can be actually put onto your textbook and then go through our analysis. Okay, so you can start from now on, start analysis with me. Okay, did you guys enjoy the journey? It was pretty fun today, right? Yeah. So, do you really believe that we can, manufacture this kind of a micro machine, and we can try this kind of testing, right? The machine that I explained to you before this was actually movable machine, but this doesn't have to have any movable part, right? Instead, it needs to have the part where heating is possible, right? So it's another interesting machine that we can actually deal with. So remember, this result is the result of experience piled up over many generations of your seniors. This is really precious result, okay? But anyways, we are honored to actually do this kind of analysis on this system using our heat transfer knowledge. Okay, so how can we analyze this machine? These are all given conditions. Well, we probably need to agree upon some kind of assumption. Well, would there be any kind of radiation? Yes, there might be through this little gap. But remember, this thickness is only 0.5 microns. So radiation occurs between two surfaces. So surface that is looking at each other here is very small. So we'll assume that, well, the radiation is negligible. It'll be very small. What about conduction through other parts? Well, there might be conduction through this thermal pass here. Would there be any conduction? No. Why not? Well, because look, this temperature, 300 Kelvin, is constant over all exterior area. If the temperature is constant, would there be any heat conduction? Not at all. So you don't need to be worried about this conduction. So the only possibility of heat transfer is conduction through this little element of carbon nanotube, which has diameter of only 14 nanometers. Amazing, amazing, right? And we are interested in finding the what is it? Thermal conductivity of carbon nanotube. Okay. Again, pH is not given. We have to find it. TS is given, right? And we'll start this interesting analysis. Well, if you think about this situation, you can draw a circuit diagram. That is the beauty of our analysis, right? Circuit diagram from high temperature, TH, to TS. Why do we use TS? Because we say that this is the sensing part. Sensing part. These two parts, elements, are identical with each other. On the left hand side, we let the current flow and generate the heat. Okay? On the right hand side, we don't let any current flow. Somehow we can measure this resistance, and the resistance change will represent the temperature change. Because platinum
resistance will actually increase as temperature increases. How much is it? It's about 4 ohms increase per 1 kilo ohm of resistance per 1 degree Kelvin. It's not, doesn't look too much, but it's a pretty reasonable value which we can measure with precision electronics. I'll talk about such electronics later on, okay? But today, let's assume that we can measure it, okay? So TS, sensor, temperature, is given, okay? And in between these two, well, there's the carbon nanotube path with, well, resistance of the carbon nanotube. And resistance, I say, is thermal resistance, right? Thermal resistance of carbon nanotube. And out to the outside, through the supporting element, right? T infinity is right here, happen to be there, right? And the other supporting element is like this, thin and long, long and thin, T infinity again, and here T infinity again, and here T infinity again, because both sides they are T infinity same with each other. We don't need to be worried about this heat conduction. There will be no heat conduction at all. And how does the heat generate? QH, right? The heated part in the QH is provided. And how much was it? It was the 11.3 microwatts. If you take a look at your textbook, you'll find it out. Okay? And what happened to this QH? Well, the half of QH will actually move to upside, right? Upper side. And the other half will move to the bottom side, okay? Sorry, it's not gonna be QH. The heat generated will be Q, sorry. And Q is actually 11.3 microwatts. Micro 10 to the minus 6 power, okay? And through this support, okay, there will be the heat conducted to outside, and the other heat will be conducted outside. If you put them together, let's say that it will be the heat conducted outside at high temperature side. So the heat conducted outside to the upper area will be total heat conducted at the high temperature area, the half of it. So this will go up. And the other half will be QH over 2 as well, because they are symmetric. And the heat conducted from the sensor side, like the same way, will be 2 over Q up and QS over 2 down. And what do you think about this point? Do you remember Kirchhoff's law? Korean, well, in Russian it's Kirchhoff law. Kirchhoff. K-I-R-C-H. Hoff. Kirchhoff's current law. It's not a law actually. It's just an observation of a fact. There's a flow coming in, and this flow will go up and down. That's it. Right here, there's a flow generated. This flow will go up, down, and then to the right. So what will be this flow? Well, take a look at this. This flow is half of QS. This flow is another half of QS. So what is this QS, the flow here? There's no other way of this flow, going out. So the only flow that occurred through this carbon nanotube would be additional 2. That will be QS. Right? So you can set up, an equation right away that explains the whole situation. Q generated will be used by heated area as QH. The half will go, the other half will come down, but the other one will be QS. And QS will actually flow up and down like this. So this is the result of Kirchhoff's current law. Indeed. Interesting, right? Because this is electrical circuit analysis, you can just apply this kind of law. You can not only apply this kind of Kirchhoff's law here for the electrical circuit analysis, but flow analysis as well. Any kind of flow, in compressor flow, will follow the same principle. So the resistance, thermal resistance of this upper part will be R, I would say SUP, supporting element, and the other three supporting element will share the same thermal resistance because they're identical structures, right? The thin beam with the this composite structure, platinum and the silicon nitride composite. Okay, so how can you calculate this thermal resistance of supporting element? Well, if you think about this composite, this supporting element consists of platinum thermal pass, right? Platinum thermal pass here from the core, and the shell, silicon nitride that actually encapsulate this platinum. So silicon nitride thermal pass. How does this thermal pass? How do these thermal paths are actually interconnected, parallel to each other? Parallel, right? One goes in, the other will come from the outside, but looks like they are in parallel, configuration. So you have the parallel thermal pass, right? One in the core. Well, I would use thermal resistance of platinum, and the other area in the exterior of this platinum that encapsulate this platinum, thermal resistance. Sorry, the thermal resistance of what? Silicon nitride in parallel. So if you just put them together, what will be the resistance, thermal resistance of the whole thing? Well, this is parallel combination, so you would have to use 1 over R GT and 1 over R silicon nitride, right? It's exactly the same way that you use to analyze electrical circuit. Why? Because electrical circuit is flow of electrons. Because a thermal circuit is flow of photons, same particles. So what is the thermal resistance of platinum? Well, how does it look like? If you think about your previous idea, it will be 1 over the thermal conductivity of platinum, and proportional to the length. The longer the length you have, the larger the thermal resistance you have. Right? Like the same way, the longer the length of the electrical resistance you have, the larger the electrical resistance you will have anyway. So what is this length? That length is the supporting length, right? Supporting structure right here. This length, right? This length. There are 4 such kind of supporting structures, right? So it will be L supporting structure divided by what? Area, right? Area of what? Platinum, right? So if you just plug in all these things, how can you calculate? Well, let's use some calculator. So I've already tried this calculation. Let's see. Be clear? Okay. And what was our length? L supporting. So let me clear everything. L supporting was 250 microns. In terms of meters, it will be 250. 1 micron is 10 to the minus 6 meters, right? So minus 10 to the minus 6 meters. There we go. And what was the thermal conductivity of the platinum? KPT was given 71.6, right? I've already put it, right? What was the thermal conductivity of silicon nitride? 15.5, right? 15.5. Was it 15.5? Let me check it out. Yes, it was 15.5. Okay. So 15.5. So what do we need more? Thermal conductivity and area of the platinum. Area of platinum was, well, what was the thickness? Thickness, I remember it was 0.2 microns. And what was the width? Width was only 1 microns. Was it written? No, probably. Let me take a look at our picture. Yes, it was written. Yeah, it is the, it's not written. Let me write it down. Platinum, the size was 0.2 microns. Please take a look at your textbook. And the width was 1 micrometers. Okay, so we'll just use that number. And so the area is 1 micron by 0.2 microns. That's the area in terms of meter square, right? And the area of silicon nitride is, well, you need to take a look at the picture. The total area minus platinum area. That is silicon nitride area, right? So total area is 0.5 micron by 3 microns, right? So just punch in 0.5 microns by 3 microns. Make no mistake in terms of the units, minus platinum area, right? And that gives you silicon nitride area, all right? And now we have the thermal resistance of platinum. That will be 1 over heat transfer, thermal conductivity of platinum times and length of supporting structure divided by area of platinum, right? And what is it? That's 1.7458.0 times 10 to the 7th power. I'm gonna write it down. It's gonna be 1 point. So let me just move it. 1.7458 times 10 to the 7th. Well, what's the unit? R is thermal resistance. Voltage divided by current. Voltage is temperature. Temperature is Kelvin divided by current. Current is watt. So it'll be Kelvin per watt. Okay. And what about the thermal resistance of silicon nitride? It will be again 1 over thermal conductivity of silicon nitride. Length same, right? The supporting structure is the same. Area different. Area of silicon nitride we have already calculated, right? So just punch in this number, and right here, thermal resistance of silicon nitride is nothing but 1 over KSM, which is we already provide this number, times length of supporting structure 250 microns divided by A silicon nitride. Right? And yeah, that's 1.24 times 10 to the 7th power watt. 1.2407 times 10 to the 7th power Kelvin per watt. Okay, so what will be the R support? Well, you can calculate it. Again, you can calculate our supporting structure will be, SUP will be 1 over RPT, right? Be careful. Plus 1 over silicon nitride, which we have already calculated. It's going to be 7.25 something to the 10 to the 6th power. So let me write it down. Supporting structure our supporting structure will be 7.2. What is it? 5 to 7. 5 to 7 times 10 to the 6th power Kelvin per watt. Well, look at the order. This is 10 to 7, 10 to 7. This is 10 to 6. What kind of lessons can we learn? First of all, the thermal resistance of platinum part and thermal resistance of silicon nitride part, they are comparable, which really means that you cannot ignore one or the other. You have to consider both. And second, because they are connected in parallel, their total thermal resistance will be lower. Heat can be dissipated better, rather than being dissipated along the silicon nitride or platinum, both together in parallel. The heat can actually conduct it much better, right? So the order is one order lower here. Okay, that really makes sense. That really makes sense. Well, now is the time to look at thermal resistance of this carbon nanotube part. So how can you calculate? Well, carbon nanotube, our carbon nanotube will be, again, following the same definition, 1 over thermal conductivity of carbon nanotube, which we want to know, times length of this carbon nanotube, which was 5 microns. If you take a look at your textbook, and the area of carbon nanotube, which we can calculate, obviously. So we know this, but we don't know this. Okay, and by definition, resistance is voltage divided by current. What plays the role of the voltage? Yes, temperature difference. What is the temperature difference? Temperature difference between left hand side and right hand side. TH minus TS, right? So TH, we don't know, by the way. TS, we know we can measure it, as I said, using resistance change at different temperature. Divided by QH. Do we know QH? We'll see. Yeah, we'll see. Probably not yet, right? So if I just circle unknowns, unknown, and probably unknown, it's not explicitly given, right? Yeah, so how can you find that out? First of all, we have the current flow, which needs to be like this. Well, again, whatever heat that has been generated will be transmitted to up and down and across this carbon nanotube, right? That is QS. And half of it will be used to move up, the other half will move down, okay? That's our equation right here. So you can set up a equation for the left hand side. What happens? Half of a heat that moves up through the supporting element will be the voltage or the temperature difference between this point and this point. This point TH, that point T infinity, right? So it will be TH minus T infinity. And what is the resistance? Thermal resistance of supporting element, which we have already calculated right here, okay? And so here, you can calculate TH. TH is nothing but QH over 2 times R supporting, right? You can use this equation, plus T infinity. We know T infinity, we know R sub. Oh, we have to find this out. Where can you find this out? Let's take a look at this. If you take a look at right hand side of the circuit, this part, right? You can set up the current equation again, right? So half of QH will be TS. TS is temperature right here, which is given, right? TS given, sorry. TS given, right? TS is given here, minus T infinity, right? TS minus T infinity, and R supporting structure. So you can calculate QS. QS is nothing but twice of this value, TS minus T infinity over R supporting. Can you calculate it? Yes. What was the TS? TS is given, right? TS was 308 point something. I forgot. Where is it? Let me take a look at that. 308.4 Kelvin. So TS was 308.4 Kelvin. And what is T infinity? I would use T infinity, right? It was 300 Kelvin. And how do you calculate QS? Twice that difference divided by our support, right? So I would just put, what was it? QS, right? QS equals twice times TS minus TI divided by our support, which we have already calculated. And that's gonna be 2.3164 microwatts. So I'll just write it down. This will be 2.3164 microwatts, 10 to the minus 6 power, right? Well, so we can calculate QH. Why? Because we have this equation now. So how can you calculate QH? QH is nothing but Q minus QS. That's what we intended, right? And Q was given in your textbook 11.34. I forgot. What was it? 11.3 indeed. 11.3. 11.3 minus this value, right? So if you just plug in right there, if you just calculate it, what is it? QH was 11.3 microwatts minus minus 6 minus QS, and that will be about 9 microwatts. So I'm going to write it down. 9836. 8.9836 microwatts. So now we have a good view about how this heat is flowing. You know, you have this circuit right here. The heat generated here is 11.3 microwatts, and the heat conducted through this supporting element is about 9 microwatts. It will be only fraction of it. It's only about 3 microwatts that has been conducted through this nanotube. Small. However, look, this nanotube is so small, so thin. With this thin structure, you can conduct such amount of heat that is substantial. That will be large, very large. So just for your reference, normally, what will be the thermal conductivity of good conductors like metals? For instance, like copper, you can find out from the website. You know, copper thermal conductivity will be 380 something. It's about 400 watt per Kelvin. Okay, watt per Kelvin. So let's calculate what kind of a result we have regarding this carbon nanotube thermal conductivity. Okay, so we are almost there. We know this QH done. Now we just have to calculate the TH. How can we calculate? Because we know QH, you can use this equation to calculate TH. So let's use our calculator again. What was the equation? Half of QH times R sub plus T infinity. Half of QH. So TH equals half of QH times what? Times R sub times thermal resistivity of supporting element plus T infinity. Wow, pretty high actually, 332.577 degrees Celsius. So this will be 332.578 Kelvin. Right? How much is it? It's about 60 degrees Celsius, right? So 60 degrees Celsius on the left hand side, about 30 degrees Celsius on the right hand side. The heat is flowing by the temperature difference, right? From the hot side to the cold side. Hot, cold, there's a conduction, right? Well, so we're done. We're almost done now, really. So what is the thermal conductivity of carbon nanotube? Where is it given? It's given anyway. Yeah, it's right here. Right? So you can calculate indeed KCN. KCN, how much is it? KCN. Let's see. So therefore, you take a look at all these things. KCN will be LCN over ACN times QH over GH minus TS, right? So let's try it. KCN equals LCN. LCN is given 5 microns, right? It's 5 microns, but the gap size, right? Over ACN, the carbon nanotube area given. Well, let me calculate it. LCN is 5 microns, right? And the cross-section area of carbon nanotube will be a quarter times diameter of carbon nanotube. Let me give the diameter. Diameter was 14 nanometer, right? 14 times 10 to the minus 9 power. Amazing, very small, right? And so area of carbon nanotube will be a quarter times and diameter times square, right? Times what? Sorry, there needs to be times pi, right? pi is already given, embedded here. So this is the area, right? Everything's ready. So KCN, you can really calculate, and that will be LCN divided by ACN times QH, we have already calculated, right? Divided by TH, we have calculated, minus TS, right? There's something wrong with this. Was it QH? TH? TH? That's right. TS? That's right. And QH? That's right, I guess so. And ACN? I guess so. LCN? Right. So let me try again. KCN equals to LCN divided by ACN times QH divided by QH minus TS. Sorry, there's something wrong with this. Oh, sorry. Oh, yeah. This needs to be QH, but KCN, you take a look at this. Where is it? RCN, right here. This should be, isn't it QS? Sorry. That's QS, right? Yeah, the heat is flowing through this guy. So QS is a current right there. So if you want to calculate RCN, it should be delta, temperature difference, divided by current, heat flow. That's QS. So you need to use QS here, sorry, instead of QH. So we have same equation again, but instead of QS, QH, we have to use QS. Okay, now we have a result. KCN is about 3,112 Kelvin per watt. Sorry, watt per Kelvin. That's thermal conductivity, right? Watt per Kelvin. Remember, as a comparison, thermal conductivity of copper, one of the most well-conducting material, is 384, if I remember correctly, watt per Kelvin. Look,
It's 10 times greater than the most well-conducting material on Earth. Isn't that amazing? So graphene, carbon nanotube, these kind of superstructures can conduct the heat very well. Why? We'll take a look at later on. There's a atomistic explanation, very small scale, nanoscale explanation that actually account for this unusual thermal conductivity. Is it useful? Very useful. People use this kind of material for highly conducting materials actually. Okay.